Supervised learning is one of the foundational methods in machine learning. At its core, it involves teaching a machine to make predictions or decisions based on labeled data. This means that for every input, there is a corresponding output that the model can learn from. The goal is to create a mapping function between inputs and outputs, allowing the model to make predictions on new, unseen data. Supervised learning is broadly classified into regression and classification, each with distinct purposes and application. Regression. Regression is used when the target variable is continuous. The objective is to predict a numerical value based on input features. For example, predicting the temperature on a given day based on weather conditions like humidity, wind speed, and cloud cover is a regression task. In such cases, the relationship between the input features and the output is often assumed to be a continuous smooth function. The key characteristics of regression problems include continuous outputs. Predictions can take any real value, such as temperature, stock prices, or blood pressure readings. Evaluation metrics. Common metrics to evaluate regression models include mean squared error, mean absolute error, and R squared, which means how will the model's predictions align with the actual values. Regression problems are particularly useful in scenarios where precise numerical predictions are essential for decision making, such as in financial forecasting or engineering simulation. We'll be covering a simple linear regression program that predicts house prices based on their sizes. Linear regression is a basic machine learning algorithm that models the relationship between one or more input variables and a target variable using a straight line. To start, step 1 involves importing the necessary libraries. We use NumPy for numerical operations like handling arrays and PyPlot for creating plots and visualizations. From the scikit-learn library, we import functions like train, test, split to split data into training and testing sets, linear regression to perform regression analysis, and mean squared error to evaluate the model's performance. Next, in step 2, we generate synthetic data to simulate a real world scenario. Using NumPy, we generate 100 random house sizes and calculate their prices using the linear equation y is equals to 4 plus 3x plus noise, where x represents the house sizes and noise is random variability added to make the data more realistic. By setting a random seed, we ensure reproducibility of the generated data. This means that every time the code runs, the same random values will be used, providing consistent results for analysis and debugging. The generated data gives us a sample but practical dataset to train and test our model. In step 3, we divide the dataset into training and testing sets using train, test, split. This step is crucial for evaluating the model's performance on unseen data. We use 80% of the data for training and reserve 20% for testing. Then we initialize a linear regression model and train it using the training data. The fit method learns the relationship between house sizes and prices by determining the best fitting line through the data. Once trained, the model is ready to make predictions. Using the predict method, we estimate house prices for the test data, producing predicted values that we can compare with the actual test values. Finally, in step 4, we evaluate the model's accuracy using the mean squared error (MSE), which measures the average squared difference between the predicted and actual values, with smaller values indicating better performance. The result is printed for quick assessment. Additionally, we visualize the results using matplotlib. A scatter plot shows the original data points, while the regression line illustrates the model's predictions over the range of house sizes. This plot helps us understand how well the model fits the data. By combining data visualization, model training, evaluation, and generation, this program demonstrates the fundamental steps involved in linear regression, making it excellent introduction to machine learning concepts. Classification. On the other hand, classification is used when the target variable is categorical. The goal is to assign each input to one of a predefined set of classes or categories. A classic example of classification is determining whether an email is spam or not spam. In this case, the model learns to distinguish between the features of spam emails and non spam emails, assigning new emails to one of these categories. Key characteristics of classification problems include categorical outputs. Outputs are discrete classes such as a yes or no, spam or not spam, or even multiple classes like cat, dog, or bird. Evaluation metrics. Metrics like accuracy, precision, recall, F1 score, and ROC are used to evaluate classification models. These metrics help understand not only how often the model is correct, but how well it performs under different scenarios, such as when the data is imbalanced. Classification is widely used in various fields. In medicine, it helps diagnose diseases based on symptoms. In security, it identifies fraudulent transactions. And in computer vision, it classifies images into categories. Differences between regression and classification. While both regression and classification fall under supervised learning, they differ fundamentally. First, nature of outputs. Regression outputs are continuous, while classification outputs are discrete. Applications. Regression predicts values such as sales or demand, while classification categorizes data such as identifying emails or classifying images. Model evaluation. Regression focuses on error metrics like MAC, while classification focuses on metrics like accuracy and precision. Logistic regression is a supervised machine learning algorithm used for classification problems, predicting discrete labels like flower species based on input features. Step 1 begins with loading the IRS dataset, a well known dataset in the machine learning industry, containing measurements of sepal length, sepal width, and petal length for three flower species: Setosa, versicolor, and virginica. The dataset comes preloaded in scikit-learn and we extract its features and labels. Here, X or the features contains the numerical measurements and Y or the labels contain the corresponding flower species encoded as integers for 0 for Setosa, 1 for versicolor, and 2 for virginica. In step 2, we split the data into training and testing subsets using the train test split function. This division ensures that we can evaluate the model's performance on unseen data after training. We allocate 80% of the data for training and 20% for testing with a fixed random state for reproducibility. Training data is used to build the model while test data is reserved for evaluation. By splitting the data, we simulate a real world scenario where the model encounters new data and ensures that it doesn't just memorize the training set. Next, in step 3, we initialize and train a logistic regression model and we set max iter is equals to 200 to ensure the algorithm has sufficient iterations to converge. The logistic regression works by finding the best fitting curve or a logistic function that separates the classes from feature space. Using the fit method, the model learns the relationship between the features and labels from the training data. After training, we use the predict method in step 4 to classify the test data. The predictions are stored in ypred representing the species the model thinks each test sample belongs to. Finally, in step 5, we evaluate the model's performance. First, we compute the accuracy score, which measures the percentage of correctly classified samples out of the total test samples. A higher accuracy indicates better performance. We then print a classification report using classification report, which provides detailed metrics like precision, recall, and F1 score for each class. These metrics give us a deeper insight into the model's strengths and weaknesses for each flower species. By combining data preparation, model training, prediction, and evaluation, this program offers a comprehensive introduction to logistic regression. Challenges in supervised learning. Supervised learning is powerful, but it comes with its own set of challenges: overfitting and underfitting. Overfitting occurs when the model learns patterns too specific to the training data, reducing its ability to generalize. Underfitting occurs when the model is too simple to capture the underlying patterns of the data. Data quality and quantity. Supervised, supervised learning heavily depends on having sufficient high quality labeled data. Insufficient or noisy data can significantly impact model performance. Imbalanced data. When one class dominates the dataset, classification models may become biased towards the majority class. Techniques like resampling or weighting can help address this issue. Supervised learning through regression classification is cornerstone of machine learning. Its versatility allows it to be applied to a range of real world problems, from predicting future trends to making decisions based on past data. By carefully understanding the nature of the task and addressing challenges such as overfitting and data quality, supervised learning models can deliver powerful and actionable insights.